Hello everyone. Today I will present our work, expanding mmWave Dataset using annotated LiDAR data for human pose estimation. Human pose estimation, or HPE, aims to predict the human skeleton, including the positions and connectivity of body joints or key points. It is a fundamental task with broad applications, such as robotics, human-computer interaction, action recognition, and many other human-centered sensing systems. Recently, mmWave radar has attracted increasing attention for HPE. Compared with RGB cameras, mmWave radar naturally captures 3D information, better protects user privacy, and is robust under different lighting conditions. In mainstream mmWave-based HPE methods, raw radar signals are usually processed into point cloud sequences, which are then used as model input. However, existing mmWave HPE datasets are still scarce and lack diversity. This limitation appears in two major aspects. First, point cloud attributes are limited because datasets are often collected using similar devices and environments, leading to limited variation in detection noise, point density, and motion sensitivity. Second, human poses are also limited, because subjects often perform simple motions while facing the radar. As a result, models trained on these datasets may generalize poorly to unseen real-world scenarios. A natural solution is to expand existing mmWave datasets. Unlabeled mmWave data is easy to collect because it does not require manual pose annotation. Meanwhile, LiDAR-based HPE datasets are already widely available and often contain more diverse poses. However, LiDAR and mmWave point clouds have fundamentally different sensing characteristics. Therefore, the key question is, how can we use unlabeled mmWave data and annotated LiDAR data to expand mmWave HPE datasets? Previous data expansion methods mainly follow two directions. Some methods synthesize mmWave data from videos. These methods can increase pose diversity, but the generated point clouds usually still follow the distribution of the original mmWave dataset. Other methods use LiDAR point clouds to supervise mmWave point cloud enhancement. However, they require paired and jointly labeled mmWave LiDAR data, which is difficult and costly to collect in practice. Our work makes three main contributions. First, we propose a trained pseudo-label estimator to annotate unlabeled mmWave point clouds. Second, we propose a closed-form converter that translates LiDAR point clouds into mmWave-like point clouds. Third, we combine these two components into EMDUL, a full dataset expansion pipeline. The final expanded dataset is then used to train the HPE model from scratch. Now I will introduce the proposed method, EMDUL. The main idea is to expand a small labeled mmWave dataset from two directions, using unlabeled mmWave data through pseudo-labeling, and using LiDAR datasets through point cloud conversion. This page shows the overall pipeline. We start with an input labeled mmWave dataset and an annotated LiDAR dataset. The LiDAR point clouds are converted into mmWave-style point clouds, forming a converted dataset. Then, the original labeled mmWave data and the converted data are combined to train a pseudo-label estimator. This estimator annotates the unlabeled mmWave data. Finally, the original labeled data, converted LiDAR data, and pseudo-labeled mmWave data are merged into the final expanded training dataset. For unlabeled mmWave data, we train a pseudo-label estimator. This estimator is trained using two types of supervision. On labeled data, we use the standard mean-squared error loss between predicted and ground truth skeletons. On unlabeled data, we introduce an unsupervised temporal consistency loss, called UTCL, to make the predicted pseudo-labels more reliable and temporally stable. The motivation of UTCL comes from the motion detection mechanism of mmWave radar. Because mmWave point cloud formation relies heavily on the Doppler effect, moving body parts are more likely to be detected, while static body parts may produce fewer points. Therefore, if a predicted joint is surrounded by points, it is likely to be moving. If it is far away from detected points, it is more likely to be static. UTCL uses this prior through two terms, dynamic consistency loss, which encourages motion for likely moving joints, and static consistency loss, which encourages zero flow for likely static joints. Next, we convert annotated LiDAR datasets into mmWave-style point clouds. The conversion pipeline consists of 4 steps. Noisy point addition simulates environmental noise. Flow-based point filtering simulates the mmWave motion detection mechanism. Random sampling reduces point density. Finally, noise injection simulates the lower spatial resolution of mmWave radar. Together, these operations make LiDAR point clouds more similar to mmWave point clouds. Flow-based point filtering, or FPF, is the key step in the conversion pipeline. It estimates a motion flow value for each LiDAR point based on the skeleton motion. Then, points with lower flow magnitude are removed with higher probability. This mimics the fact that mmWave radar is more sensitive to moving body parts. As a result, the converted point cloud keeps more points near dynamic regions and fewer points near static regions. Now I will present the experimental results. We evaluate whether EMDUL can improve both in-domain performance and out-of-domain generalization for mmWave human pose estimation. We use 2 mmWave datasets, mmBody and mmPhi, and 2 LiDAR datasets, hMPair and LiDAR human 26M. To simulate a data scarce setting, only 10% of the mmWave training data is used as labeled data, while the remaining 90% is treated as unlabeled mmWave data. The full LiDAR training set is used as the additional annotated LiDAR source. We evaluate performance using 2 standard metrics, mpJPE and pmpJPE. Both are reported in centimeters, and lower values indicate better performance. We compare against several settings: training with no data expansion, training with LiDAR expansion, and training with both LiDAR data and pseudo-labeling using a mean teacher baseline. This allows us to evaluate the effect of each component and the full EMDUL pipeline. The main results show that EMDUL generally outperforms the baselines. Compared with training only on the small labeled mmWave dataset, EMDUL improves performance across most settings. The improvement is especially clear in out-of-domain evaluations, where the training and testing datasets come from different mmWave datasets. This indicates that EMDUL does not only improve fitting to the original dataset, but also enhances generalization by increasing both pose diversity and point cloud attribute diversity. The visualization results further confirm the quantitative findings. In these examples, red joints indicate errors larger than 10 cm, while green joints indicate smaller errors. Compared with the baseline predictions, the model trained with EMDUL produces more accurate skeletons, especially in challenging cross-dataset settings such as mmPhi to mmBody and mmBody to mmPhi. We also conduct ablation studies to understand the contribution of each component. For pseudo-labeling, using both dynamic and static consistency gives the best result, showing that the 2 parts of UTCL are complementary. For LiDAR conversion, each augmentation step contributes to performance, but flow-based point filtering is particularly important because it directly models the motion-sensitive nature of mmWave radar. To conclude, we propose EMDUL, a dataset expansion approach for mmWave human pose estimation. EMDUL uses a pseudo-label estimator with unsupervised temporal consistency loss to exploit unlabeled mmWave data, and a closed-form point cloud converter to transform annotated LiDAR data into mmWave-style training data. Experiments on multiple mmWave and LiDAR datasets show that EMDUL effectively improves both accuracy and generalization. Thank you for watching.